Okay, hi everybody. I hope that you're all doing well. I wanted to briefly give you this supplemental explanation of an interesting and common problem in interpreting two-way tables. I noticed a couple of examples of it on the homework, but it's also something that I wanted to spend more time explaining in the lecture from this past week. We ultimately sort of ran out of time. And unfortunately, because the SSCC lab was having some tech issues, I ended up delivering the lecture from the desktop computer in there, and I wasn't prepared to record from there, and Zoom may not have been installed. So I wasn't able to record the lecture. Hopefully most of the lecture is fairly self-explanatory because I do write fairly careful lecture notes. But because this was a case where I actually drew on some of my lecture notes from last semester, a lot of this explanation, although it is written down in the link that I give in the lecture notes, I said a lot of things out loud that might have been slightly hard to follow, and it's written in a couple of places. So I thought I would just record this brief, and I think in some ways kind of fun little piece. This is not something that you need to watch in order to do well on an exam or the project, but if you had some trouble with this on the homework, it may be useful to watch at least the first part of it, which runs only about 10-15 minutes when I try to dry run through this. And then if you're interested in going a little bit deeper and learning a little bit about the literature on this problem, you can continue watching. And if you want to see sort of one of the theorems that underlies all of this, which is Bayes' theorem and a proof of that, you're welcome to watch until the end. All things told, this would take only about an hour. And many people tell me that they can watch my videos at about 1.5 speed because I do have a distinct way of speaking that is very slow, as you probably have noticed. So let's dive into some complications of two-way tables. First, I wanted to note something that I may not have called adequate attention to during the lecture on Tuesday or on Monday, which is that there's some further notation hell in this part of statistics and computing. And unfortunately, that's something that is common throughout all of mathematics, as I noted in the lecture notes. One of the reasons that we use all those Greek letters that might seem sort of obscure or pompous is that it turns out there's just a limited number of symbols using Roman or Latin letters and Arabic numbers that to represent a whole range of ideas. So this is a case where we actually have a kind of non-standard character here, this straight line, but this straight line means two different things, and I wanted to make this clear. So when we've met this straight line before in statistics, we've been understanding it as the or operator. So do this or do that. But in statistics proper, it actually is the conditional operator. So what this says really is P of A given B, or in other words, that's what this represents. So it means the probability of A once we know that B is true. For example, the probability of rolling a 5 is 1 in 6 for a fair die because you've got 6 faces and 5 is only one of them. But if I tell you that I've rolled a fair die and I hide the result from you, but I tell you that it's odd, if I'm maybe trying to help you like have an easier time guessing for whatever reason, then you have a 1 in 3 chance because you know that you've only got 1, 3, and 5 to pick from. And this should be possible faces rather than possibly. So this can be confusing, and I wanted to call attention to it. Conditional probability can get very complex, but this notation is simple and it's fairly intuitive to understand. Once you know certain information, a lot of times the probability of some other thing happening is significantly changed. And you can think about it both in the sense of once you know some information or once some event has occurred. And actually that's tied to a big distinction in statistical ways of thinking that I'm not going to get into here. So if that sounds a little fuzzy, don't worry, there's some dispute about that, and it partially depends on your perspective. Okay, so the main thing I wanted to show you in this first part of the lecture is this. Basically, we calculate two-way tables correctly when we compute the conditional probabilities in a way that makes sense and easily answers the question that we're interested in. And the best way to do that is to condition the probabilities on the thing that you think is the predictor. Now, that said, some people in the homework made this really interesting discovery that is a sign of really good independent statistical thinking. And other people may have wondered about this, and I wanted to call some attention to it and just give a more systematic exposition. And I made this point in lecture, but I just want to call attention to it one more time. Two-way tables actually cannot be calculated to have wrong conditional probabilities. That's an important point. So you can never, it would be sort of alarming, right, if you could somehow make a mistake in calculating conditional probabilities. So you can't do it in a way that will give you information that is false, but you can give information that might be misleading. And I want to give you an example of how it takes a little more work when you've calculated conditional probabilities in a way that's not exactly how you meant to do it. And I can also show you, however, a way to uncover the correct information. So let's say we're interested in this question of unions and race, and we'll suppose that we're interested in which racial group, using the modified but still sort of imperfect GSS groups that I showed you how to compute, has the highest degree of union friendliness, or at least propensity to join a union. And you'll see why I'm using race again in a moment, because it's a case where there's a pretty skewed distribution. So it helps us see why this has some upshot. So I'm going to run a little bit of code here. I'm going to first call in the better race data. We've saved this before as a class, so you should have access to this. If not, you can simulate this just using the race variable in the GSS. It won't make a big difference. Now, I do some stuff here that you've been practicing a whole lot. Basically, I take the union variable on the GSS. I notice that there are several possible values that basically mean you or your spouse or both as a member of a union. So I decided to compile those together into a dummy variable called union fam. And it looks like this. This is the original variable on the rows. This is the new variable on the columns. Now let's go ahead and tabulate this new race variable that we made last time, which remember has possible values of white, black, Hispanic, and other, which is a problematic category, I know. And again, I would encourage anyone who's interested in this question, that would be a great project. I just stopped with making it there because I did that myself for a project many moons ago, and that fulfilled the conditions of the assignment. But if I were going to go further with that project, I would certainly probably try to make that variable a little bit better. So you're welcome to try that on your own. That's a fine project. So let's go ahead and look at this. And so I want to show you how calculating, in this case, column conditional probabilities, or in other words, calculating the percentages down the columns, could potentially be slightly misleading. And what I want to show you first is, what if you just hone in on this column here, union family? If someone tells you, well, 73, and in fact, about 74% of union families are white, and they don't give you any other context. Now, for you all who are sophisticated statistical thinkers at this point, you might immediately start wondering, but you can see probably how someone who maybe hasn't been trained to think in this way or hasn't thought about things in this way in a long time might find that possibly misleading or at least confusing, right? So what if they said, well, that sounds like a really big number, right? And I suppose, that probably means that white people are actually the ones with the highest propensity to join a union in the United States. And even if they don't immediately think in that way, it might still be unclear what to do with this information. It might be clear that it doesn't actually answer the question of which race group in the US is most prone to join a union, but it still might not be clear what to do with that kind of information. And the reason this is misleading, or potentially misleading, is that we've calculated column conditional probabilities when we really want row conditional probabilities. In other words, we want to figure out, conditional on your race status, what is your probability of being non-union or being a union member, right? And so that said, this information in this table does help us answer that question, but we have to be a little bit careful. And what a lot of people notice in the homework, and I'm very proud of you all for noticing this, is that the way to get that information is to compare this conditional distribution of races across union statuses to the marginal distribution of race, or to the distribution of race conditional on some other value of union. So here, if we look at the total distribution of races, we do see that whites are only about 72.5% of the population with a little bit of rounding, but they're about 74% of the union population. And so that does indicate that whites are slightly more likely to join a union. But that's actually just a little bit of a coincidence here. And certainly it's not like they're 74% more likely as perhaps someone who doesn't feel totally comfortable with this way of thinking. Maybe that would be the impression they would get at first. And I'm not saying that to be condescending at all. I'm saying that as a way, basically on the assumption that if you know a lot about something, you probably don't know a lot about a whole lot of other things. And experts in those other areas are, generally speaking, kind enough to present information to you in a way that's clear and doesn't mislead. And that's part of what it means to live in a robust democracy, right? We have to try to make information as accessible to people as possible, and not just preach on high. So that's kind of what I'm trying to suggest here, is that we should really try to make sure we're presenting information in a way that allows other people to get in on the fun and participate in the discussion. So here, that would be sort of misleading to just present this number, even though it's not totally wrong. And let me give another example where we can see that it could be pretty misleading to just give this little datum, because we're going to see in a little bit that there's other groups, and actually by a hair, and this is easier to see in bigger and more reliable data sets, that Black workers also are disproportionately likely to be union members. So they're 17% of the union sample in the GSS 2018, but they were only 16% of the population, or the sample in this case, pardon me. Now you might say, well, the percent difference is larger for white workers here, but it's not actually about the raw percentage point difference here, it's about the multiplicative difference. And we'll see that you can do away with the problem of having to figure that out, which can get a little bit complex arithmetically, or maybe just conceptually, if we calculate probabilities in a more sensible way. Conversely here, because Hispanic folks in this version of the way we recomputed race are a relatively small part of the population and the sample here, it's not totally clear from the start like what it would mean to say that out of all union workers, we estimate that Hispanic workers are probably around 5%. That's really small, yeah, but if we don't have a clear idea in mind of what the marginal distribution of race is like, then maybe this is actually disproportionately large. Maybe it's disproportionately small. We would need to know this kind of information to say. Another thing we could do is also, and this is especially useful when there's only two possible outcomes of the outcome variable, the thing that is maybe wrongly here, or sorry, not the outcome variable, but the predictive variable, which is maybe shouldn't be used as the predictor here. We could also compare to the other condition. So we could compare the distribution of race conditional on non-union status. And we can see here that, yeah, it's a little bit higher for white workers, it's a little bit higher for Black workers, it's a little bit lower for Hispanic workers, and it's a little bit lower for people that we put in the other bucket, which again is problematic and imperfect. There's ways to improve that. So that's another way to think about it, is we could say, well, they're a slightly larger percentage of the non-union population, and so that indicates that there's some difference here. But we could also kind of just do away with all of this if we just calculate things in a slightly different way. And what this doesn't do is allow us to get away once we calculate, let's say, row conditional probabilities, where we condition on the thing we believe to be the causal variable. It doesn't allow us to avoid the need to compare individual conditional distributions to other conditional distributions and marginal distributions, but it makes it a little bit clearer how we can answer the question. So the point, the big takeaway here, and later in this video I'll prove this, if you want to keep watching, you don't need to though. Again, none of this is strictly necessary if you already understand what that is. It is true, looking at this, that if Black workers and white workers are in fact disproportionately likely to be union workers, they're also going to be a disproportionate share of the union population. But one, we can see it's hard to assess which one is actually more likely or has a higher propensity. And two, we can see you can get some really misleading results in either direction, like we saw with white workers or with Hispanic or Latino workers, by just focusing on elements of this conditional distribution without mentioning this marginal distribution. By the way, you've probably figured this out, and I know I've mentioned this before, but marginal distribution just means the unconditional or the overall distribution. It's called the marginal distribution actually because it appears in the margins of two-way tables. So nice little bit of etymology there. When we look at row conditional probabilities, we see that the answer emerges a little bit more clearly. Notice that you can now just directly compute which groups are most and least likely to be members of unions. And we do see here that, technically speaking, a slightly higher share of Black workers are union members than any other group here, although white workers are not far behind. And again, this is a small sample. I checked this with some census data, or data that the Census Bureau collects from much larger samples. And I'm not using survey weights here, so that makes all of this slightly unreliable, but these data are consistent with other data that I know to be true. But these differences aren't really huge. So if we focused, as we did before, on just this value here, white workers are 74% of union families, we would get a possible picture of the kind of relationship of race and union status that would be substantially misleading. Here, as I mentioned before, we should still compare, like we shouldn't fixate too much on this row or on this row or on this row without comparing it to other conditional distributions. But it's a little bit easier to directly assess the question here. By the way, this happens to be a particular case where there really isn't much of a relationship between unions and race, or just between the two variables, I mean to say. So we can actually do a chi-square test here. Let's do that now. Oh, mistake there, sorry. And we can see that we have a p-value of 0.8, or in other words, we would see results this extreme or more about 80% of the time if the null of no relationship between the two variables were true. In other words, results this extreme are really not evidence against the null hypothesis, which is virtually always that two things are not related. So in other words, we don't really have any evidence that there's a relationship between the two things. So that's the basic idea. I hope this was useful to you in understanding how it's kind of a complex message, I guess, that I'm trying to put forward, but it is both the case that two-way tables can't really give information that's wrong. So you're free to compute them in different ways, but it might make more and less sense to compute them in this way or that way, depending on what your purpose is. I also now wanted to go ahead and give you this other example, and this will take a little while to explain. So you're welcome to watch if you're interested. You don't need to. This is going to be more or less a deeper dive into a kind of canonical problem that effectively boils down to this injunction to not confuse inverse conditional probabilities. And then at the very end of the video, I'll show a proof of this fact I mentioned here, that two-way tables, again, can't really be calculated incorrectly, but it is the case that if you calculate them going the opposite way that you maybe intend to, sometimes you can get results that seem weird but are compatible with calculating them the correct way. So that I'll just go into a more theoretical discussion. But I wanted to first set up this interesting problem here. This is a pretty famous study, and it's one of several very similar studies that have been conducted over the years. It's more complicated, but it could be useful to you, and you may have heard of it before. I'm going to use this particular paper that I've taught before by Britta Anderson and her colleagues, appeared in 2013 in the Journal of Graduate Medical Education. And it basically was an experiment. It's a consensual experiment. They sent a survey to medical residents in some pretty prestigious places, and they asked them to answer basically a little bit of a stylized example about a woman receiving a test for breast cancer. And content warning, I'm going to discuss cancer just because I didn't want to change the example too much. And they asked people basically, what should the woman take away from this set of numbers about who tests positive and who has cancer? And what's the probability basically that she will have cancer just because she's gotten a positive test? By the way, I wanted to make this super clear. This example is not intended to pick on medical professionals. It's just a striking and often cited study. So I think it's striking and often cited because the stakes are just very high. So I'm lucky. A lot of people in academia are lucky that we can't really make a lot of catastrophic mistakes on a day-to-day basis. We can do stuff wrong, but honestly, we just have less responsibility in a lot of ways than people who work in the medical field. So I'm saying that out of humility. This is not, an attempt to dunk on people who are medical professionals, but it's just a good example of how your ability to understand statistics can sometimes have weighty consequences. I also wanted to make this secondary point. Well, two secondary points. One, I'm sure in any comparable field where people are probably expected to understand some kind of basic statistics, but maybe that's not always super well understood. Doubtlessly, that's true in every field that people are coming up short in some ways. And it's true in my field, it's true for me plenty of the time. My secondary point was that I'm sure in practice, a lot of medical professionals are not really letting this maybe shaky grasp of some of the finer points of two-way tables get in the way of their excellent work. Like, you don't have to actually understand the nuances here to come up with good diagnostic criteria. So I know it's kind of a long preamble, but since I'm going to present this example at some length, I did want to mention that this just happens to deal with the medical field, but it's not meant to pick on medical professionals. Okay, so now let's go ahead and go on to the setup. So 10 out of every 1,000 women in this stylized example have breast cancer. Again, these are made up numbers, it's just a scenario. Of these 10 women with breast cancer, 9 test positive. Of the 990 women without cancer, about 91 nevertheless test positive. So the test has a false positive rate of about 9.2%. A woman tests positive and wants to know whether she has breast cancer for sure, or at least what the chances are. What is the answer to the question? And it turns out that about 26% of the residents surveyed get this correct. It's a typo. The most common wrong answer was one form or another of 90%. And I think this mistake, the authors don't really speculate too much, but it seems to stem from possibly two problems. One, the confusion of the sensitivity of the test, or in other words, the probability of a positive test, given that you really do have cancer, which is very high. Maybe the confusion of that with the probability of cancer, given that you have a positive test, which is the thing that we actually want to find. So those are inverse conditional probabilities. And second, it might have to do with the confusion between a low false positive rate, or in other words, the probability of a positive test given no cancer. And we see above that it's only about 9% or so, with the conditional probability, probability of cancer given a positive test, which again is the thing that we hope to find. So let's turn and see this in Stata.
So I'm going to show you how you can do some cool stuff using Statas, basically using fake data or using random number functions and that sort of a thing. So what we're going to do first is just make sure the data set is clear. Of course it is, because I started with a blank Stata, but it's good practice. Now I'm going to set up 1,000 fake observations. I'm going to make an index number for these observations. Now I'm going to use the truth syntax here to tell Stata, give a positive or a 1, not a positive cancer status, but just a 1 on the variable cancer, because we haven't labeled it yet, to the first 9 individuals. So 9 of the 10 cancer having individuals will be the first 9 people. Now we're going to go ahead and make a value label. Let's call it carcinogen. We'll say 0 means you do not have cancer, 1 means you do have cancer, and we'll label the values. And next we want to go ahead and stipulate that 100 out of the 1,000 people, or 10%, will test positive for cancer overall. And so that was basically given to us by the problem. So overall, well, sorry, that's not given by the problem, but this is something you can infer. Basically, 10% of people will test positive. So that includes people who have false positives and people who have true positives. That number works out to be exactly 10%. Okay, so we're going to go ahead and label the values of the test variable here as well. And now we need to pick one unlucky person to have a positive cancer status, but a negative test. And so since the people with negative tests were those under 101, let's just pick person 101 to have, positive test for people under 101. So the first person with the negative test, 101, is that individual. We'll give them cancer. Now, just for the sake of making this more realistic, and so that we can examine this a little bit, I want to go ahead and sort these observations in random order. Right now, the order is not random. I actually use the order to assign people to different statuses. So we're going to make a sort order where we take basically a random value function using the uniform distribution. So basically, Stata will just pick numbers at random by randomly dropping down or simulating randomly dropping down like a stone or something on the number line. And we'll make the results of that the sort order variable, and we'll sort by this random number. Now let's make an ID variable that's now independent of the assignment of treatment and control. Remember, the old one was not. And we'll get rid of the original ID variable. And let's just look at some observations. And you can see here, most people do not have cancer and test negative. We do have one person who had cancer and tested positive. And if you run this yourself, you'll get different results. We have another person who had cancer and tested positive. So far, nothing too weird here. This is someone who had no cancer and tested positive. So this would be a case of a false positive. And here is another false positive. So that kind of feels intuitively like we've set this up correctly. So now let's go ahead and calculate row conditional probabilities and see what we find. Oops. So you can see here that when we calculate row conditional probabilities, we see again that you have overall a 90% chance of testing negative, 10% chance of testing positive. But the real action here is in these rows here. So if you don't have cancer, you have a 90% chance of testing negative. Or in other words, the conditional probability of a negative test, given that you do not have cancer, is 90%. And the conditional probability of getting a positive test, given that you do not have cancer, is about 9%, or 9.2 if you round. Conversely, if you do have cancer, the conditional probability of a negative test is 10%. So if you have cancer, at least you're likely to have it identified. And the conditional probability of having a positive test is quite high. So the test is picking up actual cases of cancer well. It's also correctly rejecting people who have no cancer. It's correctly rejecting them a high percentage of the time. And so the way you might think about this is then, well, okay, so if I have this positive test, well, the probability of me getting a positive test if I didn't have cancer was only 10%. So that's kind of scary. Maybe I actually have cancer. And conversely, the probability if I did have cancer that I would have a positive test was 90%. So isn't that evidence that I have cancer? That's kind of terrifying. Well, it turns out this is a pretty extreme case of conditioning on the wrong thing. So the way to think about this is what we want to do is remember what we want to condition on. Actually, what we know about you is not that you don't have cancer or that you do have cancer. What we know about you is that you tested positive. So we want to condition on your test status. And then what we want to do is see, conditional on you having a positive test, what is your probability of having cancer? And you can already tell from the numbers probably, although I want to show it explicitly, that it turns out it's actually a very low probability of having cancer. You have a 9% chance of having cancer. You have a 91% chance of being cancer-free. Now, notably, just as we saw before, this is consistent with calculating probabilities in the other way. So if you had a negative test, your probability of not having cancer would be nearly 100%. So that's good, right? So basically the problem of a false negative is more or less negligible in this data set. There's one person who was unlucky enough to have that. But if you had a positive test, you still have, although it's relatively smaller, you still have a good conditional probability of not having cancer. This example is kind of confusing at first because it's not immediately clear why the first way of thinking about it is wrong. And what I wanted to point out here is that it is true that only a small percentage of cancer-free people test positive, but you can get caught up in this sort of mistakenly hyper-individualistic way of thinking about it, where you go up here and you say, what's the probability that I'm going to be one of those 9% of people who test positive, even though they don't have cancer? But probability can be confusing in that way. Let me give another example. Let's say that you have a height that is, let's say if you're a guy, I think the mean height is like 5'11". Let's say if you're a guy, you have a height that's 5'11". I'm using the biological sex binary, so forgive me for that. I'm not trying to disregard a broader range of gender expression, but just to make it simple, you might have a height that's exactly 5'11". Now that's the most common height for men, right? Biological men. But that doesn't mean that there's a very high probability of you being exactly 5'11", right? Because it might be the case that, okay, 5'11" is the mean height, but there's not a ton of people who are exactly 5'11". And actually, you might even know this interesting fact that if you have a truly continuous variable, the probability of observing any particular value is actually 0. So the area under the curve of any particular point, if you're envisioning a probability density function, the area under the curve of exactly any point is in fact 0. It's a little confusing, but the math there can get kind of complicated and heady. If it doesn't make sense that it's 0, you can certainly imagine, however, that it's probably very small, right? If you imagine the sliver, the tiny little sliver that you would shade for exactly 5'11" and 0.0000000, percent of an inch or whatever, right? It's kind of improbable. If you could measure height to, the millionth decimal or something, surely there would be incredibly few people who are exactly 5'11". So probability can sometimes be confusing in that way. So yes, it is true that if you look at these four cells basically give all four possible outcomes here, assuming that you're, say, in a 1,000 person hospital, or just assuming these stand in for larger numbers. Yes, it is pretty unlikely for you to be in this group, right? The probability of you being in this cell specifically is, you can think about it as 91 over 1,000, right? So out of any group, you're much more probable to be in this group here. You don't have cancer and you test negative. But if we know that the test has a certain false positive rate, someone's going to end up here, right? If you think about it from the perspective not of a single individual, but let's say you're someone working at the hospital, you're a clinician, you're a women's health specialist or something like that, you're not going to panic if you know your stuff when you see some people test positive, because you're going to say, well, we know that the test produces false positives. It's just a failing of many tests. It's common to a wide variety of medical tests. And so someone has to be those people, right? It doesn't mean anything about that person's actual probability of having cancer. So it can be a little confusing to look at it that way. But I think it's helpful to think about that height analogy as well. This is a little different in that in the height analogy, you're really at the central tendency if you have the mean height, even if very few people have your exact height. Here, this is clearly not, and there's not really a central tendency for qualitative statices, but clearly this is not like anything approaching the central tendency. The mode, you can calculate the mode for qualitative variables, so this is clearly not the mode. But it still is the case, however, that even if only a certain percent of the population is going to have this outcome and that percent is small, some people, if it is true that a certain percent of the population has that outcome, some people have to have that outcome. So yes, it's unlikely for it to be you. But in a certain sense, to pick another analogy, it's a little bit like saying, what's the probability, what was the probability, 10 years before you were born, that you would have the exact name that you have, and you would live in the exact place that you live, and be in UW-Madison at this point, and be in this class. Like, all that stuff is also, technically speaking, very improbable, as was any outcome. So sometimes that can be a confusing way to look at it, and it's better to focus on conditional probabilities. Here's an analogy that I often use that might help. So let's turn to a happier subject. Let's turn to the subject of excellence in women's sports. And let's figure out the probability of any woman athlete being a top 10% basketball player in high school. Well, that's pretty easy to figure out. It's 10%, obviously, by definition. And let's actually just relabel the variables in this gloomier example to match this new sports analogy. And what's going to be the analogy of cancer? Well, let's use something a little bit happier again. Let's use having cancer. We're going to turn that into its happier analog of being a WNBA player or a professional women's basketball player. And we'll use positive tests to mean you were a top tier high school athlete, or top tier just means top 10%. So let's look at these data now. And we can see here we have the same numbers if we compare the raw frequencies, but we've relabeled them. So basically, if we look at this with row conditional probabilities, we can see kind of a similar story to what we were looking at before. If you were not in the WNBA, you weren't a professional women's basketball player, you had a high probability of not being a top tier athlete, and you had a low probability of being a top tier athlete in high school. And overall, the probability of being a top tier athlete in high school was also small. Conversely, if you were a pro athlete, you had a very good chance of being a top tier athlete in high school. There was only one person that somehow made their way into the league without having been a top tier athlete, which makes a lot of sense. But you can see how this is a nice analogy, because it's clear why the way of thinking involved in, well, only a small percent of cancer-free people test positive. It's clear why that line of thinking is wrong. So let's think about that here. So if I tell you, okay, this person isn't in the WNBA, so the probability that they were a top tier athlete in high school is super small. And maybe that means that they're actually secretly in the WNBA somehow, right? Or in other words, they secretly have cancer, quote unquote. But the point here is that that actually isn't implausible at all. By definition, there has to be a top 10% of high school athletes. I mean, as long as you're rank ordering athletes somehow, and there's all kinds of organizations that do that, which is probably a little bit creepy, but whatever. So like if you were in the top 10% of athletes, you're being recruited by colleges, like that top 10% has to exist. It's just a mathematical fact. But being a player in the WNBA is extremely improbable, right? It's just not a thing most people are able to make work. So there's nothing inconsistent in saying, yes, it's improbable that this person was a good high school athlete in that way, by definition, by mathematical construction, basically. That doesn't mean, however, that they have to have a good shot at being a professional player. So it neither means that they must secretly be a pro athlete if they were good in high school, and neither does it mean that it was impossible that they were a good athlete in high school and that they must be lying. It's just that they are part of this rare, but again, statistically, it's basically bound to exist. They're part of this rare group. So just because a certain group is unlikely to be observed, that doesn't mean that anytime you observe it, there must be something fishy going on, because you should still observe the group some of the time, right? And so one way to think about this that I like to use is it's kind of like this. You can imagine pouring rocks through two filters above a tub. The first one has small holes, the first filter, and the second one has tiny holes. And the tub is almost perfectly sealed so that almost nothing gets into the tub besides these rocks. So it is unlikely for the first rock, for any particular rock to pass through the first filter. So there's a low probability of that happening, period. And yet, almost no rocks get into the tub, and yes, almost no rocks get into the tub without going through either sieve. But sorry, I was writing really bad here. So yes, almost no rocks get into the tub without going through either sieve. But that says nothing about whether rocks that get through the first filter can easily get through the second filter. So to make that analogy clear, it is improbable for someone to be a good high school athlete. And yes, almost no pro players were bad athletes or mediocre athletes in high school. But that still doesn't mean that just because someone was a good pro athlete in high school or a good athlete in high school, that they're going to be a pro athlete. So analogously, that doesn't mean, just because it's rare to have a positive cancer test when you don't have it, that really does not mean that you probably have cancer just because of that. And we can do the same thing here. We can once again show that no matter which way you calculate the two-way table, there's no wrong way to do it, just a confusing way. So let's look at this here. So now we see conditional probabilities that are calculated in possibly a more meaningful way, because in this case, just like before, the thing that we do know, basically, or the thing that we might maybe not know, but the thing that maybe is causal, I should say, is probably your high school athletic status, right? That presumably to a large extent determines your later athletic status. So if you were a top tier athlete, you still have a 91% chance in this constructed example of not being a pro player. In fact, it's much, much more likely that you don't make it to the pros, unfortunately. So you can see all we did was change the way we calculated the conditional probabilities. And yet we seem to have a slightly different story, at least until you really understand this kind of paradox result. So that said, though, I wanted to show that these results are consistent with what we saw before. Very much like with the Union and Race case, it is true that having been a top tier athlete in high school does make you relatively more probable to be a pro athlete. So here, the conditional probability of being a pro athlete on you being a top tier player is 9%, but the marginal probability of being in the pros is 1%. And the conditional probability of being in the pros if you were a mediocre athlete in high school is only 0.11%. So this is consistent with the common sense idea that yes, if you are a top tier athlete, it makes you significantly more probable to be a pro athlete down the road. But this more clearly shows that that's still a rare outcome. Whereas if we calculate it here, again, this is kind of an inverse way of thinking about it. I mean, technically any conditional probability has an inverse, but this is kind of a sociologically inverse way of thinking about it, in that we're using something that happens later in time to predict something that happened earlier in time. That's not always wrong to do, but it can be confusing and it can lead you to sometimes make some mistakes. So here, this made it seem like, well, it's really rare for you, if you're not in the WNBA, to have been a top tier player. So were you really a top tier player, or are you sure you're not secretly in the WNBA? But those would be unwarranted conclusions. It just stems from this kind of funny way of calculating this. Whereas here, it's clear that even though it's rare to be a top tier athlete, we know that by definition, 10% of people are going to be a top 10% athlete, or 10% of people that play sports are going to be top 10% athletes. But that still doesn't make it likely for them to be in the pros. So that's where I wanted to wrap this up really quickly. One takeaway here is basically this. I'm going to all this just to put it on the screen. So the main takeaway is this. In epidemiology and in life course settings like this, where you're thinking about what's going to happen to you in the future, people are oftentimes more interested in the absolute probability of some event or in their own outcome, rather than, for instance, how unlikely it is for someone to be in their shoes, so to speak, or on basically like whether or not some particular status, such as testing positive or being a top tier player, makes them relatively more likely to have some outcome. So instead of saying, well, the probability of a positive test given you have cancer is much higher for the probability of a positive test given no cancer, or it is unlikely for anyone to be a great high school basketball player, they may want to know things more like, well, is the probability of cancer given a positive test something I should worry about? Or do I have a chance to play pro ball if I am really good at high school ball? And in both cases, we are left with this problem that, yes, we have some condition, such as being a top tier high school athlete or having a positive test, that does make some outcome, one good and one bad, much, much more relatively likely by huge factors. But that can be misleading because that is combined with, and you probably have figured this out, but if you work out the Bayesian arithmetic, it's combined with the fact that the underlying outcome, whether good or bad, is so rare in the population that this basically, the relative increase in the probability of it still means a low, it's not technically an absolute probability, I should say, because it's conditional probability, but it still results in a low conditional probability, not considering comparison to another conditional probability. So there's this interesting fact that we saw before, just to bring this all home, that yes, it's good to compare any particular conditional distribution to other conditional distributions, but also sometimes that can be misleading as well, because it might be that while there's a relative difference, there's a big relative difference, the actual difference, sorry for that, really doesn't matter that much at all, right? Because the outcome is still unlikely. And in this case, it's not even that unlikely in this constructed example. 9% isn't meaningless. It's not something you would want to, bet the farm on for sure, or not bet the farm on, as the case may be. But as a practical matter, if you're dispensing medical advice or career advice, you would want to say, yeah, that's a pretty unlikely outcome. So all that's to say, you always want to act with nuance here. You always want to think about a problem from a variety of different angles. So thanks for watching, everyone. I'm going to append to this a little proof of this that also goes through Bayes' theorem that you might find useful, but I hope this has helped you in understanding some of the complexities of two-way tables. Thanks, take care. Okay, folks, so I now wanted to go ahead and show a brief proof of the fact that you can uncover information from a two-way table that is calculated incorrectly, basically, or has its conditional probabilities calculated in a way that might be unintuitive. And to show that, I need to show Bayes' theorem to you very briefly. And this is a really useful thing to know, so it's not bad to know. Again, this is not essential for our course, but it's something that you'll find useful at higher levels, and it's pretty, again, if you tell someone you're interested in statistics, for instance, they might ask you about this pretty quickly. So it's a good thing to know. So I want to first start with something pretty simple that you may have seen before. I want to represent the probability of possible outcomes of some kind of real world situation using a sample space. So I'm going to draw a box here. Pardon me, I need to connect really quickly, but I'm going to draw a box effectively. And then what I'm going to do is consider this box or rectangle to be a representation of all possible outcomes of an event. So any event in the world can be understood as this slightly not rectangular box, basically, or as some subspace here. And now I'm going to draw an event here that represents, well, some set of outcomes. So this could be rolling a 1 or a 2 when you roll a fair die, for instance. It's not exactly proportional, but you get the idea. So this represents some kind of event, and this space here, we'll call S, is the sample space, and this space here is the place where all events in this world happen. So here we could say, let's call this event A, and we can say that the P of A, probability of A, appears to be, oh, I don't know, maybe 1 in 8. And so the size of these basically circles, or we could draw them as rectangles, whatever, in the sample space S is proportional to their probability. Or in other words, you could basically just take the area here. And it really doesn't matter what the units are. You could just take the actual area of this circle, just literally as big as it is on the screen, and divide it by the area of S and get the probability. Okay, so now let's imagine another event that overlaps to an extent with A. So let's go here and let's call it B. And we'll label that here. And we can crosshatch in B as well. And so B is a little smaller than A. So let's say the probability of B is about 1 in 9. Okay, so now you can see that these events have some overlap. And so in particular, it could be the case that maybe A, for instance, means that you roll some kind of really complicated die, like a D&D die or something. I don't know a lot about that stuff, but it's kind of 20-sided die. And B is some kind of event in the game that could happen as a result of rolling this die, but it might not. And so the ways in which it could happen without the die roll are represented by this area here that's not overlapping with A. And then the ways that it could happen with the die being rolled are these things here that overlap with A. Similarly, we have to assume that this event A can happen without triggering B, and that's represented by this area here, but that some of the time that does trigger B effectively, and that's right here. So these are, should look like a Venn diagram to you likely. Maybe to pick another example, one that's a little bit less silly, especially because I don't know that much about that type of game. You could say, again, to pick a sports analogy, which might be a little bit more familiar, you could say, to use our WNBA example again, that it's the case that if a certain player or set of players score a certain number of points, that maybe that doesn't result in the outcome their team wins, and that's represented by this area here. But some of the time it does result in their team winning here. And then conversely, you can say the team can win without those players scoring, and that happens in these ways here, but sometimes they'll score and win. slightly artificial because winning and losing are really the only possible outcomes apart from a tie or a forfeit or something. So these circles should probably be bigger, but that's just a technicality really. Okay, so what this lets us do, this way of thinking about things, is to understand how to calculate conditional probabilities. So let's say I want to first think about the conditional probability of A, or let's start with B given A, because that's how we've been talking about it. So we'll say that the conditional probability of B given A is equal to what? Well, if the conditional probability is like saying, what's the probability of B when A is true? Visually, that's kind of like saying, instead of thinking about B as a member of this space here, think about part of B, this part here, as a member of this space here, as a subset of this space. So how could we write that out? Well, what we could say is if normally the probability of B is equal to, say, equals the area of B over area of S, then the probability of B given A is equal to the area of B and A. We'll write B and A like this using the, pardon me, intersection symbol here. And we'll say that it's over now the area of A. And so we can write that more simply like this. So what if we now divide the area of B and A by S? And now you might be thinking, well, that changes the numbers. And indeed it does. But remember that in algebra, we are allowed to divide the numerator and the denominator of a fraction by the same number without changing it. So now let's go ahead and divide the area of A by S, or by the area of S. And actually now what we've done is calculate the probability of B and A in the numerator and the probability of A in the denominator. So we can now write that like this. The probability of B given A is equal to probability of A and B over the probability of A. And you can see pretty immediately that this same logic is going to hold for A and B, but reversed. And I won't even walk through that because it's a little bit tedious and you'll probably understand pretty immediately. There's nothing that changes. We're just looking at it a different way. I guess maybe I'll call attention to just this one point here, which is now we're considering this intersection not as a member of this subspace A, but this subspace B, but the same general principle holds. The numbers are going to change slightly, but that's not a big deal. So you would, of course, generally expect that, the probability of, let's say, it raining, given that it feels a little wet outside, is different from the probability of it feeling a little bit wet outside, given that it's raining, right? It might be the case that it's almost impossible for it to feel wet outside unless it rains, depending on where you live, or it might be very likely that it does. So we can write this like this. So this is the probability of A and B now over the probability of B. Okay, so for those of you who are familiar and comfortable with algebra, let's move this over, by the way, you might notice something pretty useful here, which is that we have in the numerator of both of these things, we have the same quantity. And so we can rearrange these formulae like so by isolating the probability of A and B. So we can say that the probability of B given A times the probability of A equals the probability of A and B. And the probability of A given B times the probability of B also equals the probability of A and B. Okay, now we can set these equal to one another. And let's be lazy and just do this. And let's finally say we wanted to calculate the conditional probability of B given A. So therefore, I want to kind of keep the picture in view here. I guess it's going to be a little bit hard. Let's do this. We can now finally say that the probability of B given A equal to the probability of A given B times the probability of B over the probability of A. And this result is known as Bayes' theorem. Bayes was an English geneticist or protogeneticist. It's usually not written with the apostrophe because it's difficult to remember where the apostrophe goes when the name already ends in S, as many years of Catholic school taught me. Yeah, this with the apostrophe or not, this is Bayes' theorem. So this is a really famous result. And you may have seen this before, even if it's not immediately clear why this is useful. It's useful for an enormous number of applications. One thing that it shows us immediately is that the probability of B given A and the probability of A given B are not going to be the same unless these two quantities are the same. Or in other words, unless the marginal probability of B and the marginal probability of A are identical. So let's pick an example that we've been working with so far. So that would mean that the probability of you having cancer, given that you have a positive test, only equals the probability of you having a positive test, given that you have cancer, which you'll recall was very high, if the probability of you having cancer is the same as the probability of you having a positive test. Right, so you can see how this fits into the formula that we derived above. So we let B here be cancer, we let A be a test. So we said that the probability of A given B, or the probability of a test given cancer, is equal to the probability of B, or the probability of cancer, over the probability of A, or the probability of a test. And since these two things, the probability of cancer, we said in our example before, was only 1%, and the probability of a test was actually 10%. So because those two are very different numbers, that means that these inverse conditional probabilities are not the same thing. So that's pretty useful to know. So I've written out here one interesting implication from this that I think is worth noting. And I went out ahead and wrote all this out, so I spared you the tedium of seeing this written. So one thing to note is if you start with the presumption that the probability of you being white, given that you're a union member, is larger than the probability that you're black, given that you're a union member, which is what we saw before, it turns out that if you algebraically rearrange this using Bayes' theorem, so here we rewrite the probability of you being white, given that you're a union member, as the probability that you're a union member given that you're white times the probability that you're white over the probability that you're a union member. We do the same thing for black folks here. And then we multiply both sides by the probability that you're a union member, getting it out of the denominator of both sides. And then we also move over the probability of white by dividing it. So we end up with this here. Then finally we divide both sides by the probability that you're a union member of black, coming up with this term here. And then finally, we just do a tiny bit more of rearrangement to make this a little bit more aesthetically appealing. So we multiply both sides by the reciprocal of this, and we multiply both sides by the reciprocal of this. And we end up with the statement that probability of being white or the probability of being black has to exceed the probability of being a union member given that you're black over the probability that you're a union member given that you're white. So what does this tell us? All this tells us is that the difference, if it's true that you're more likely to be white given that you're a union member than that you're black, all that this tells us is that this ratio here, so the ratio of white to black Americans to the population, assuming just for convenience no other races, is something like this. But notice that that's completely consistent with this ratio here being very large. So it could be the case that the probability that you're a union member given that you're black, let's make it larger just to stylize it. Let's say it's 0.2, and let's say this here is 0.1. So this statement is still true using these stylized numbers, because on the left-hand side, this is something near 8, and on the right-hand side, this is, of course, just 2. So this is true. There's still a huge differential here. So it's still the case that you're, relatively speaking, much more likely to be a union member if you're black than if you're white. And all that matters for this to be true up here is that you can't be so much more likely that it overtakes the white-black ratio in the population. So that's one useful way to rewrite this that I think is pretty interesting. Now, what if we start actually from this second point here? And here I'll just go through this algebra really quickly. Forgot that I wanted to mention this. Let's start from this. Probability that you are a union member given that you're black exceeds the probability that you are a union member given that you're white. And we can again use Bayes' theorem here to rewrite these. So we'll say that this is the probability that you're black given that you're a union member times the probability that you're a union member, the probability of being black, and the same for whites. And we can now do a very similar thing where we get the probability of union membership out of the numerator in both cases. And then we can just do a tiny bit of rearrangement. So let's say we want to do this here. So once again, this shows us that you can have the kind of information that you see in a miscalculated two-way table or in a confusingly calculated two-way table that shows that there really isn't a wrong way to calculate a two-way table, but it's just interesting to see what kinds of numbers are in fact compatible with other kinds of numbers, even though it doesn't seem like that should be possible. So what are we looking at here? Well, what this tells us is that if it's true that you are more likely to be a union member if you're black than if you're white, all of that forces is that the ratio of you being black given that you're a union member to you being white given that you're a union member has to be larger than the overall ratio of black to white individuals. So again, using our stylized and kind of made up numbers, we said before, let's say this is elevated just for the sake of simple numbers. And this, oh, sorry, I was messing this up. So the probability that you're black given that you're a union member, we actually didn't compute that already. But let's just say that it's something like 0.25. Let's say that this then is 0.75 or something. And so if we come here, before we said we presumed that in the population, this is a ratio here. Now, again, you can see that this is true because this on the left-hand side is about 2 and 7 roughly, whereas this is about 1 and 8 roughly, a little different. But clearly this is true intuitively. So what is the upshot of this? What's the point? Well, it can still be the case, as you see here with these numerator and denominator, that you're still relatively more likely to be white given that you're a union member relative than black. But it is the case, however, that this ratio is tilted more in favor of black workers than the overall ratio of black to white workers here, right? So this is consistent, this idea that you are relatively more likely to be a union member if you're black than if you're white. That is consistent with basically the probability that you're black given that you're a union member to the probability that you're white given that you're a union member. That ratio has to be bigger than the overall ratio of black to white individuals, but that doesn't mean that the actual numbers involved here, such as the ratio of black to white union workers, isn't still tilted very heavily in favor of whites. So it's kind of complicated, but basically Bayes' theorem here can help us see how it is true that a miscalculated two-way table has to sort of, if looked at carefully, encode the truth, so to speak. So it has to be the case, even if you calculate basically race conditional on union membership, that a careful reader can uncover the fact that black workers in this scenario are more likely to be union members. But that can still be sort of misleading, and that's compatible with it being the case that you are more likely to be white if you're a union member, just as a function of the fact that you are more likely to be white overall. So that's a nice use of Bayes' theorem.